Good evening, everyone. So, I hope I am audible to everyone.
Yes, sir.
Yeah, thank you very much. So, let me start. I'll be sharing my screen. Okay. All right. So, before starting, quick introductions. You might be knowing that the course is a MOOC course, online course, which is is floated by NPTEL. The instructor for this course is Professor Jayant Mukherjee. He is from IIT Bombay. He's in the Department of Electrical Engineering there, and he works on his area of interest, area of specialization is RF, RF front ends. Okay, he works in analog engineering there. So this course is a very basic level course, and it is intended uh, for the people who are just starting into the vast this vast universe of circuits. Okay, so this is an analog circuits course. Here you will learn a lot of things, basic things about analog circuits, and I hope you enjoy this course. Okay, now who am I? So I'm a tutor for this course. So my job is different from the instructor. So instructor for this course is a professor. My job here is to conduct these weekly sessions. I hope I'm sure that all of you must have been notified by the the NPTEL about these arrangements till by now. So I'll be conducting these live tutorial sessions. So what I will be doing is in these tutorial sessions I will be solving some problems on the content on the basis of the content that has been taught a week before. So today, since this is the very first tutorial session, I'll be I'll be covering the week one content. Means I will covering questions or problems based on week one's content. Okay. So what I want from you is to be is to interact with me. Okay, these sessions are not supposed to be like I will be speaking and you will be listening. That is not the objective of this of these sessions. The main objective of this session is for you to interact so that we can all benefit from these sessions. Okay, you can ask your questions, your queries about the course, about the content that you might find difficult. Okay, I'm here to answer all those questions. If I do not if it happens that I don't know some answer, I'll be definitely coming back to you with the answer in the next session. Okay, so please don't just yeah, you will be getting a recording for this session. So the recordings will all be provided as YouTube links. Okay, all of these sessions will be recorded. So today my session will be recorded and it will be provided to you as a YouTube link. Okay, I'll be hosting these recordings on my YouTube channel, and the links for which will be provided to you. If not today, then probably in the next week or so, you'll definitely be getting them. Okay, so I am sure that all of you know that there are two tutors for this course. Okay, one is me and the other one is Henil. Okay, he's conducting his sessions on Monday. That is yesterday. He conducted his first session on yesterday. Okay, yesterday he conducted a session 6 to 8, and my session is weekly Tuesdays. Okay, from 6 to 8. So you pick one whatever you like. So you can join any of these two or you can join both of these two, doesn't matter. If at all, if you're not able to join, you can always go back and watch these sessions on YouTube. Okay, so I hope that concludes the introduction part. So now let me share my screen and I will be starting with this week's content. Huh. Yeah, Kamalesh, yeah, you have a question? A lot of people have raised the hand, I see. Yeah, Kamalesh, you have a question? You have raised your hand. All right. So it looks like it doesn't have a question. Fine. Yeah, the recording is on. So my screen, is it visible to you? one of you can say
Yes,
something.
sir. Visible, sir.
Yeah, thank you, thank you, thank you. That would be all. All right. So, just as a formality, let me good reintroduce myself. Okay. I mean, these are just formalities, but need to be done. So, my name is this course is an NPTEL course. Its name is Analog Circuits, and the instructor for this course is Professor Jayanta Mukherjee. I hope you all have seen him till by now. He is a professor in Department of Electrical Engineering at IIT Bombay. All right. Who am I? My name is Mayank Anupam. I am the tutor for this course. Okay, and I am also a PMRF. And I'm working in again in the Department of Electrical Engineering at IIT Kanpur. Okay. So now in this week, in the first week, these are the topics which were covered, right? Roughly. So I don't know what is your background in this. So are all of you comfortable with the concept of I mean with the concept of Laplace transforms? I'm sure you must have heard of it. And this is a very basic thing, Laplace transform. So that is something which is a definite prerequisite for this course. So assuming that you are all comfortable with this, and I see a yes in this for this question. So I'm assuming that all of you know this Laplace transforms. So I'll be moving ahead with that. Okay. So you heard, you listened, sorry, you learned about transfer function, right? So what are the transfer functions? Basically, these are nothing but, as also explained in the lecture, this is nothing but the irrational, rational, this thing, a rational fraction, a rational polynomial, which is defined, a rational polynomial relationship, which is defined between two signals. Okay, generally it is between input and output. Okay, some kind of input and some kind of output. It depends upon the context, which what you, if it is a system which has multiple inputs and multiple outputs, so probably there you have many different transfer functions. It can be defined. Okay, and it can be defined between different inputs and different outputs. Fine. So that is the transfer function. Now you also learned about poles and zeros there, right? So what was poles and zeros? So let's say this is a transfer function. T of s is equal to some uh, s square plus 3s plus, sorry, plus 2 divided by, or rather s plus 2 divided by Kamlesh, you see, Kamalesh rather, you see this, this is week one's this thing only, tutorial only. You have not missed anything till now. I mean, the one that was covered by Henil yesterday is also, I mean, there are two PMRF TAs for this course, tutors for this course. One is me, Mayank Anupam, and another one is Henil. Okay, the one that he covered, probably that is the one that you missed. Okay, it's don't worry about it. You will be getting a recorded session. I mean, the recorded YouTube link for that. Okay, all right. So let's say this is the transfer function s plus 2 divided by s square plus 3s plus 2. So can some of you tell me, or one of you tell me, what is the pole and what is what are poles in the system and what is the zero in the system?
The pole is -2.
Pole is -2. Okay, and okay, pole, you are saying pole is -2. All right. What else? What about zeros? Okay, someone is saying 0 is -2 and pole is -1 and -2. So which of these two is correct? So what is the definition of poles and zeros? So if you are given transfer function, okay, if you are given a transfer function like this, the pole is the poles are the roots of the denominator, right? So let's say you means in this case any general transfer function, rational polynomial function can be represented in this manner, right? Correct. So what is meant by poles? Poles are the roots of d of s or denominator. They are called as poles. And what are the zeros of the system? They are the roots of n of s or numerator, right? So the person who said that the pole in this system, the pole in this system is -2 is not correct, because -2 is the root for the numerator, right? I mean, yeah, -2 is also a root for the denominator also, right? But there are two roots in the system, so there are two poles in the system, okay? And there is only one zero, which is -2, okay? All right, so this I hope you understand the concept of poles and zeros. Now moving ahead, so what are you also learned about op amps, right? So probably this might be the first time that you heard about op amps, is it? Can one of you just say yes or no? Have you heard about op amps before? Okay, fine. So yeah, so this is the first time that you heard about op amps. So now that so you see, just to give you a slight background, I mean, this op amp circuits, these op amps are kind of one of the most important circuit blocks that you will ever find in analog circuits. Okay, you will find its applications are wide ranging. So the op amps here that are taught to you, they will keep coming to you if you pursue this field further. They will keep coming to you in different flavors. Okay, so op amps are one of the most important, if not the most important. They are one of the most important circuit blocks that you will ever find in the analog circuits engineering. Fine. So now for in this course we will not be going into the actual circuit inside the op amp, but you will just be considering op amp as a black box, okay, or op amp as a block, and then you will be making circuits with that. Okay, so what have you learned about op amps? So this is an op amp, right? This is what you have seen. There are two terminals, plus minus, and then there is an output terminal here, right? This is V1, or let's call it V plus. This is V minus. This is VO, right? This is what you've heard, learned about op amps. Now, in this week, in week 1, you have only learned about ideal op amps, right? So, what are ideal op amps? I mean, what are the properties which make an op amp ideal? Okay, can someone just quickly summarize the properties? What are the properties of an ideal op amp?
High input impedance,
Okay, R in. I will call input impedance as R in. Okay, let's call it R in. That should
R
tend to
in 0,
infinity. What else?
R out 0,
R out. I will
input
call it
impedance.
R out like this. It should be 0. Good. Someone is saying
High gain,
infinite bandwidth in the
high
comment
gain,
section. Yeah, correct. So high gain means what? Ideal op amp means gain should be, or gain I will denote as AV. It should be what? Infinity, right?
infinity,
Yes. What
and
else?
high common mode rejection ratio,
Good. Common mode rejection should be
infinity.
right. Good. Then
Then
someone is saying, yeah,
input
correct.
offset
Input
voltage
offset.
must be 0.
Input offset should be
Must be 0.
should be 0. Yes. Now, I hope you have watched the lectures properly. So that is why you were able to answer this. So, but again, just as a formality, what is this? What is meant by RN, input impedance? What is the meaning of this? So, input impedance means what?
Sir,
Yeah, go on, try.
input impedance high means it doesn't allow any current to flow through it, right?
Yes, good, very good. Yeah, as easy as that, right? As simple as that. So, input impedance infinity means what? The resistance that it is looking into. I mean, basically this, the two terminals here, right? The resistance that it is looking into is infinity, right? So that is why whatever voltage you connect here, it doesn't matter, it will never take any current, right? It will never take any current. So this is a very important requirement, okay, by the way. This is a very important requirement in actual applications, that something which basically the circuits which you are making using op amps should not, I mean, in general, an op amp also should not be taking any input current. Okay, otherwise there will be difficulties, there will be problems. This is a very important requirement. Fine, so that is one. What else? Rn should be great, very good. So you have answered about Rn. Now R out is equal to 0 means what? So this was actually covered in the lecture, so you should be able to quickly answer this.
So there
What is
should
when?
not be any voltage drop on the output side.
Yeah. So you all understand what is an ideal voltage source? Do you? What is an ideal voltage source?
Sir, the one which has resistance 0.
Correct. So ideal voltage source, the characteristic of an ideal voltage source is what? VI characteristic. So this, let's call it IV characteristic. So what is an ideal voltage source characteristic? It is like this, right? So this is some V, let's call V naught or Vx, right? So if it is a voltage source of value Vx, so this is how it will look like, right? So ideal voltage source does not have any series resistance in it, right? It does not have any series resistance Rs. It equal to 0, right? Am I making sense? When ideal voltage
Yes, sir.
source, whatever you connect in this side, the voltage at this point will always be what? It will always be whatever the voltage here is, right? It doesn't matter. So let's say this is your voltage source, whatever you are getting, and this is something where you are connecting, this is where you are connecting your load. So at this point the voltage will always be Vx. That is the definition of ideal voltage source. But what happens is, what ends up happening is, we never find any ideal voltage source, okay? What we do find practically is a voltage source which is again accompanied with some series resistance, okay, a very small series resistance, but still there is some, okay, there will be some series resistance here. Now what happens because of this series resistance? Now the voltage Vx here is going to be a function of the load resistance, right? Means whatever load you are connecting, let's call it RL. If RL changes, then Vx also will change, isn't it? Oh, it is very easy to see. Vx is equal to what? Not. I should not call this Vx. This will be V out. So what is V out? V out is equal to RL upon RS plus RL into what? Vx, right? There is a V out. I mean, what if the voltage that you will be actually observing? So the voltage here now becomes a function of the load resistance that you will be connecting. So something which is not desirable. If it is an ideal voltage source, if you bought this voltage source here, like if this box is a voltage source, then what do you want from this voltage source? You want this voltage to be independent of whatever you are connecting from outside, isn't it? But you see that the voltage here is not actually independent, it depends upon the resistance here. So why I was building this background is this op amps here they are also kind of like a voltage source. Okay, the voltage source, it looks like a voltage source looking from the outside, I mean from the output side. The output voltage here is only dependent upon the input voltages, isn't it? It should not depend upon anything else, correct? So it is like a what? It is like a voltage source only. It's a controlled voltage source, a term which will come across later. But for now, just understand that it behaves like like a voltage source looking from the output side, isn't it? So the a voltage source, if it has to behave like a voltage source, what is the requirement that we want? This RS, the voltage source, the resistance looking from the outside like this here, from this side, basically the resistance that you look from this side, it should be what? It should be 0, isn't it? So that is what is meant by R out is equal to 0. I hope that clears things for all of you. Fine. So that's okay. Now what is meant by so you also came across infinite bandwidth. So I will I don't know how much you will understand at this point. So let's forget this for now. I mean bandwidth. Do you understand what is meant by bandwidth? And what is the term significance of this term bandwidth? Anyone?
Sir, it is the range of frequency for which the opamp will work correctly with
Good,
the gain provided.
good, yeah. So yeah, that is precisely what it is. So bandwidth is something which you will come across later, and there will be more formal way of explaining things. But for now, understand that a bandwidth of any system, bandwidth of any system has something to do with the speed at which it can work. Okay, what is meant by high frequency? Something which is changing rapidly, right? A high frequency signal means what? The signal is changing rapidly. So if it has high bandwidth, this means that the circuit can work at higher frequencies, which means what? It can actually handle very rapidly changing signals. Okay, so the speed, you can say that in other words, you can say that the speed of the system is very high, right? Speed of the system is very high. It can quickly respond, something like that. So now it makes sense, right? You also know that the world is getting impatient day by day, right? We have moved from 2G, 1G to 5G, right? And 6G is being tested everywhere. So now, so world is rapidly changing. It is evolving, and everyone is getting impatient. So everyone wants things to be done as quickly as possible. So naturally, high bandwidth is a requirement everywhere. Okay, systems which can handle very quickly changing signals is a requirement. So infinite bandwidth is something which is only talked about in ideal op amps, but something which is always sought for. Okay, people are researching to get as high bandwidth as possible. Fine. Now high gain is a is an extremely is an extremely important requirement in op amps. Okay, in ideal op amp the gain has to be infinity, but in any op amp, in any practically usable op amp, okay, you have to make sure that the gain is actually very high. Fine. Common mode rejection is something which was also talked about in the lectures, so I'm not going to talk about it because this will again come later. Input offset, again this will be covered in week 2 again, so I'll not talk about this. For now, this is the one that this is it for op amps. Yeah, now let me talk something about op amps and negative feedback. So are you guys able to understand, were you able to understand the op amps in negative feedback? Do you understand what is meant by this term that I just wrote, negative feedback? All right, so if you don't understand negative feedback, it's okay. I mean, the term itself is important, so I'll just quickly try to explain this. So Yeah. Now we know that the gain here is infinity, right? Ideal op amp. Sanket Ramanuj, uh, I hope you are comfortable with English, or is it not? You're not comfortable with English. Sanket, you can actually turn on your speaker, turn on your microphone, and you can say, okay, it's okay,
Okay, sir.
because it becomes difficult for me to always go through the messages while I'm writing something. So हाँ संकेत, so अगर आपको हिंदी में ही समझ में आता है तो बे मतलब ये सेशंस तो हम लोग इंग्लिश में ही कर सकते हैं, ऐसा हिंदी में हम लोग कर नहीं सकते हैं। तो मेरा आपसे यही कहना होगा कि आपको अगर दिक्कत हो रही है तो फिर मतलब इसके लिए फिर आपको सेशंस के रिकॉर्डिंग आपको मिल जाएगी, सारे सेशंस की रिकॉर्डिंग आपको मिल जाएगी। अगर आपको अभी दिक्कत हो रही है समझने में तो प्रॉब्ली आप रूम पे बैठ के अपने अपने टाइम पे आप आराम आराम से यूट्यूब के सेक्शंस को, यूट्यूब पे ये वीडियोस देख सकते हैं आराम आराम से, अगर आपको
ओके।
मेरे पेज से दिक्कत हो तो। ठीक है, घबराने की
और
ज़रूरत नहीं है, आपको सेशंस के
इसकी
सारे रिकॉर्डिंग मिल जाएंगे।
लिंक कहाँ पर मिलेगी? वो पोर्टल में मिल
हाँ,
जाएगी या?
लिंक आपको प्रोवाइड किया जाएगा, एक मैसेज आएगा बाद में। लिंक अभी अभी तक एक्टिव नहीं हुआ है। ओके, इस वीक ये मेरा सेशन खत्म होने के बाद इस वीक का सारा सेशन खत्म हो जाएगा, फिर प्रॉब्ली नेक्स्ट वीक से आप लोगों को सेशंस की रिकॉर्डिंग मिल जाएगी। ओके
ओके सर,
ओके,
ठीक है सर।
फाइन फाइन फाइन, थैंक यू। All right, so yeah, now we know that the gain here is infinity, right? So if you just use this op amp like this, okay, and let's say this v minus and v plus are slightly different. Let's say this is 1 volt, v minus is 1 volt, but v plus is 1.000001 volt. So what will end up happening? Tell me. Because of that, what will be v out? Yeah, what will be v out?
Sir, it should be infinity into that point out not one.
Yeah, correct. So what is infinity into anything, any finite number?
Yeah, infinity.
Correct. So V out will go to infinity, right? So what I'm trying to say here is that even if there is, you see the difference is so minuscule, right? And it doesn't matter. It's just a number here. Any difference you take, any small difference you take, as long as it is finite, the moment it is the moment it is multiplied with the gain here, if there is an input difference at the input of the op amp, right here, okay, what will end up happening? This will either go to plus infinity or minus infinity, isn't it? Depending upon which of the v plus or v minus is greater, right? Isn't it? So to make it practically useful, it is not something which we can do, right? We cannot make sure that the two voltages are exactly same. And what is the meaning of making exactly same? I mean, no one can ensure that. Practically, you know that systems, no one can ensure that. So, how do we make sure that this op amp indeed works properly? We use something called negative feedback. And what is negative feedback? Consider yourself driving. Okay, so I don't know how many people, how many of you have drove a car or a bike.
Sir,
Yes.
sir, could you please explain with the help of circuit, sir? Means in an interview, I faced one question related to that. While if for example, if inverting amplifier is given, how can we
Yeah.
say it is in a negative feedback?
Yeah, I'll come to that. But before, let me, I mean, that is just for you, right? I mean, you wanted to understand in terms of circuits. I have to explain everyone, right? So I will come to that. I'll come to that. But before that, let me explain the concept of negative feedback. So let's say, what is negative feedback? So negative feedback is something which has to do with the, I mean, you find it everywhere. You even use it. Okay, so let's say you are riding a bicycle. Everyone has must have rode a bicycle, right? So let's say you are riding a bicycle. Now you are going very fast. You are going extremely fast, but suddenly you see that I mean, you see that you have to reduce your speed. Okay, I mean, you see somewhere that there is a traffic jam probably, and you have to reduce your speed. So How do you do that? The moment you see a traffic jam, you start to decelerate, right? You start to decelerate. But now again, while decelerating, suddenly you saw that the traffic jam is again not there. So you're gonna start accelerating, right? So what you are doing is you are actually the system, your brain is actually giving signals to your whole body after looking at the what is in front of you. What is in front of you? It is the sight, and based on that, you are making a judgment of what to do. And that is something which is what is feedback. Okay, you are giving feedback to your body. I mean, the brain is giving feedback after looking at this at what is front of you, what is in front of you. Your brain is giving feedback to your body to act accordingly. So that is feedback. Now what is negative feedback? Let me get to a slightly different example. Now let's say you are driving a motorcycle, a bike, okay, motorcycle. So now you must have seen there are always signs on the roadside which says you cannot go over 40 km per hour or 30 km per hour or 80 km per hour, like that, right? So let's say you are driving at certain speed. Okay, now your speed is suppose 70 km per hour, but now you want to reach to 80 km per hour speed. So how will you do that? You'll start accelerating, right? You'll start accelerating, and you will try to achieve that speed of 80 kilometers. The moment you achieve that 80 km speed, now you will have to be careful, right? If it goes slightly above 80 km, you decelerate. If it goes slightly below 80 km, you accelerate, right? So this is what is being done, right? Based on the requirement of speed, based on the speed that is required by you, you are actively reducing and increasing the speeds, right? So that is called negative feedback. Your system is giving, I mean, based on the requirement, you are giving a negative feedback to your system and controlling the system. Okay, so that was a motivation for negative feedback. So you see it everywhere, you just don't know it. So let's come to an example of circuits, right? So yeah, so this is a good example here. Let's say, yeah, I have connected it like this. The circuit is connected now in this fashion. Now let's say V plus is equal to 1 volt. Okay, so what can you comment about V minus V out? All these signals, all these voltages.
1 volt, sir. Based on the my reasoning is, if it is ideal, we
Huh?
can make it as a virtual ground. So
Yeah.
what and all voltage present across the non-inverting terminal, the same voltage will reflect across the inverting terminal. So
Okay.
V out would be 1 volt.
Yeah. So why do you say that? I mean, who said that it is going to be the same? The virtual short should hold here. I mean, why should it hold here at all?
Means because of the infinite gain is there. No?
Yeah. So earlier also there was infinite gain. Okay. So this is 1 volt. Should it again be 1 volt here? The gain is infinite.
No, no, sir. Because in this case we need to subtract it, right?
No, no. Yeah. So why? What happened? What special happened because of this connection? That is what I want to understand from you.
Sir, in this case, V out is connected to the inverting terminal.
Okay. So what?
Uh,
This connection is there. So what?
it means in differential amplifier. Sorry, I'm not I get exact reasoning, sir. I don't know whether it is correct or not, but I am saying.
Yeah. Yeah. Try. No problem.
Yeah,
We are
in
all here to
differential.
try.
Yeah, in differential amplifier, there would be one input would be uh, positive, one more another input, AC input would be negative, right? Inverse. So in this case, output voltage is connected to that
Yeah, it is
180
connected
degrees
here.
edge in this
So
case.
what? Yeah, so what?
Like
By
that,
the way, everyone is welcome to give a reasoning here. I mean, it is not like he has a moral responsibility to answer, right? Uh, so everyone is welcome to answer. If someone knows, please try. If you don't try, you will not learn. Yeah, go ahead. And anyone with a different reasoning, or anyone with which who also agrees with the reasoning that was just provided by your colleague. Okay, so fine. So I'll be trying to explain something. You please tell me whether you agree with it or not. All right. So this is 1 volt, right? In this case here. Now let's say I do not know what this voltage is going to be. Let's say this voltage is not 1 volt but anything else. So there is one person who has given something. So Atharv, as I said, you can also with other than commenting, you can also speak. Okay, this way I will be able to focus on writing. Otherwise, I have to always go and look at the screen. So you can maybe speak up, Atharv. All right, so probably not going to speak. Anyway, so what I was saying is, let's say this voltage V minus here is not 1 volt but anything else. Okay, okay. So anything else, let's say it is 1.5 volts. Okay, it's not 1 volt but 1.5 volt. Now what will happen, because if this is 1.5 volt here, if V minus is not equal to 1 volt but 1.5 volt, what is going to happen? What is V out going to be in that case? Okay, so V out is equal to what? AV times V plus minus V minus, right? And AV is infinity, infinity times V plus is how much? 1 volt minus 1.5 volt. So this becomes minus infinity, isn't it? So V out goes to minus infinity. Something which cannot happen in this circuit. Why? Why not? Why cannot it happen in this circuit? Why cannot V out go to minus infinity? It's because V out is shorted. No, saturation comes very late. Okay, let's assume that it can actually go. It has no problem in going till infinity. The saturation is not a constraint, but the constraint is something fundamental here. Okay, the V out here, it cannot go to minus infinity because V out and V minus are shorted, right? It cannot happen that one end of the short is going to minus infinity, other end of the short is held at 1.5 volt. That is not possible, isn't it? Right? Do you agree with me? Yeah. So in that case, what is going to happen? In that case, I mean, it also comes from the math, but it only makes sense that V minus has to be equal to V plus, right? These two voltages have to be equal. They cannot be anything else, because otherwise, if they are anything else, this voltage here, oh, my bad. This voltage here, it will go to minus infinity or plus infinity, right? And that is simply not possible, because the moment it tries to go up or down, right, a very large value, since this voltage is connecting here till this to this point, there is a negative feedback action going on. This voltage, this output is giving feedback to the input. Mind it, this is what is negative feedback here. This output here is giving feedback to the input. The moment is this output is trying to go very high in some rather in some random direction. Since this is giving feedback to the input is adjusting itself, okay, to make sure that output is not going anywhere. It is in limits. So this is what is negative feedback here in this case. So it also comes from the math that in this case you have V plus, sorry, V plus minus V minus into AV is equal to what? V out, right? So what is yeah, V plus minus V minus is equal to V out upon AV, isn't it? This is what it is. Now if AV is going to infinity, I mean as the gain is infinity, what ends up happening to V plus and V minus? They are going to be equal, isn't it? Am I right?
Yes, sir.
So this is negative feedback.
Sir,
Did you understand?
sir, reasoning is because of the difference that it results in negative in output voltage. Based on that, it is negative feedback, sir.
No. So see, the reasoning, negative feedback has to be explained. The negative feedback, the whole concept takes some time to explain. For now, you just try to understand that. Do you see a negative feedback, by the way? Some kind of feedback is, what is feedback? It is some information exchange between output and input, isn't it? That is what is feedback, roughly. Loosely, if I want to explain in a very simple term, basically what is feedback? Feedback is some information exchange between output and input. That is what is feedback. If the output is talking to the input about its conditions, about its rather difficult conditions, then this is feedback. Okay. So here also you can see that the output is talking to the input in some manner, right? In electrical terms, talking means what? There should be a connection between the two terminals. So output terminal here and input terminal here, they are connected, and that is why they are talking to each other, which means that this is a feedback. Now, why is this a negative feedback? I mean, negative feedback means something which keeps control, right? It keeps control on the. I mean, negative feedback means there has to be some. Okay, how do I explain this? I mean, this takes some time. Okay, this takes a whole lecture, a whole week's lecture to explain negative feedback properly. But just try to understand that there is some kind of feedback here, and it is a negative feedback here, and this is negative feedback. In this particular case, the negative feedback here is working in the manner that I just explained. That the moment this output is trying to go in some directions, since this is connected to the negative terminal here, I'm sorry. Yeah, since this output is connected to the negative input terminal here, this will not let it go in any direction, but it will keep it under control. Okay. But something different happens if you do the exact opposite here. Like, that is, we just flip the terminal here. Something very interesting happens. Now tell me what will happen here.
Sir, if I change the output voltage.
No, what will happen? Yeah, some of you, I mean, one of you has commented it's a positive feedback. So yeah, so what is meant by positive feedback? It is something which you have learned in your 11th class physics, which is this example. So let's say you have a ball at this point here, and let's say you have a ball at this point here. Both of these balls, as at this exact center, okay, they are in equilibrium, right? They will be, if you place it exactly at that point, it will remain there, isn't it? Both of these balls. But in the first case, even if you tweak its position slightly in this directions, in the two directions here, it will again come back, right, to the center here, isn't it? I hope you understand that in this case, it will again come back to the center. But in this case, in the second case, if you slightly give it a nudge in any direction, in any other direction, then what will happen? This will keep falling or rolling down, right? It will keep rolling down. So this is the difference between, this is a positive feedback system here. This is positive feedback, and this is negative feedback. A negative feedback tries to maintain the state of the system. It tries to maintain, I mean, how do I explain this? I mean, this is a very loosely translated statement, loosely formulated statement, but if you try to understand that, negative feedback tries to maintain the state of the system as it is, whereas positive feedback, it will try to it will try to completely destroy, it will completely destroy the state of the system. It will go into some other state if it is given a slight nudge in some direction in its present state. So basically, in the earlier case, when this was minus here and plus here, what was happening? Again, if it is 1 volt here and this is, let's say, due to some reason, the voltage V naught here, it goes to, and by the way, in this case, the voltage V naught here has to be equal to 1 volt, right? That all of you have understood, because this is 1 volt and this is also 1 volt. So that is understood. But let's say, due to some reason, this voltage V naught here, it goes to 1 point, let's say 0.00001 volt. I mean, some change has happened, some change has happened here, and it goes to 1 point this voltage, and so what will happen? Tell me. The moment this goes in this direction, it increased slightly, right? The voltage at the output increased slightly from its normal state. From the normal state is 1 volt. So what will happen? Since this voltage is connected here like this at this point, since this is connected here, so this will also go to 1.0000001 volt, right? Isn't it? And at that point, these two will be compared, right? So this is 1.00 something and this is 1 volt. So difference is negative. So what will happen? The gain is infinite. Op amp will immediately try to reduce this, right? It will try to reduce the output, isn't it? Since the input difference is negative. So you see what is happening here? The disturbance was put in some direction, right? It was increasing, but the corrective action, the action that op amp took because of this feedback here, was to make sure to nullify this this disturbance, right? The corrective action was taken in opposite direction. So this is negative feedback roughly. So more on this will be talked later in this course. So I think I have talked enough on this. A lot of time has been spent on this. So you will learn about, don't worry, you will learn about it. For now, just understand that this is this. The key takeaway which I wanted you to understand was that in the case of negative feedback in op amp, the two terminals, which are these two terminals here, they are virtually shorted. I mean, what is meant by virtually short? They are not actually shorted, but they behave like, I mean, their voltages is exactly same. Their voltage is exactly same, but they are not shorted physically. They act like they are shorted, but they are not shorted physically using a wire. There is no wire placed between them, but still they behave like they are shorted because of the negative feedback and high gain of the amplifier. Fine. So let's move on. I think that is all which I wanted to discuss here. Now quickly get on to the questions. I mean, is there any doubt here, except other than the negative feedback thing, because that will be taught again somewhere in the course? Other than this, is there any doubt?
सर हम वो पीएपीएम में सब रजिस्टर और कैपेसिटर्स वो सब कुछ लेते हैं ना, तो उसमें इक्वेशन बनाने में थोड़े थोड़े वो हार्ड लगते हैं क्योंकि
अच्छा, अभी करेंगे वो, ओके? अभी 1 घंटा वही करेंगे हम लोग. Anything else?
Fine, sir.
Yeah.
Sir, if could you please explain if it is non-ideal case also, it would be a good idea.
Non-ideal,
No, itself.
that will be talked about in the next week's content. Okay, so I'll be talking about it next week.
Yeah.
All right.
Thank you.
The effect of finite gain primarily. Okay, I will be talking about it. Anyway, so let's come on to the first question. So I'll be going in the same manner that I just quickly in the same flow that I did the recap. So first I'll be talking about this Laplace transform. So this is a question. Okay, so come on, solve it for me, please. And please note that this is how the sessions will be. I'll not be solving them. You will be solving it for me. Okay. and I'll only be helping you where you find it difficult. And please try to make sure that this indeed happens. I mean, it shouldn't it shouldn't be that from tomorrow or next session onwards none of you join just because I make it too difficult for you. I mean, just because I make it a very involved for you. So this is how it will be successful, the sessions, if you solve rather than me. All right, so a lot of comments. Fine, fine, fine. Let's see. So some people are saying that poles are 4 and minus 7. Okay, let's write some of the answers. So minus 4 and minus 7, people are saying. Okay, let's see the comments. Okay, pole is minus 7, 4 and minus 7. Oh, minus 4 and 7, minus 7. All right. And 0 is what? 0 is minus 5. And some people are saying the system is stable. Okay. Okay. And order of the system is 2. Fine. So let's see whether that is the case. Yeah, let's see that is the case or not. 1 second. Okay. So this is a what? As I said, Laplace transforms are basically you go from time domain to frequency domain, right? That is what is Laplace transform. A time domain signal which is x of t here, and all of its representation. I mean, time. What is meant by time domain signal? In this x of t is what? As a function. This signal is a function of time. It changes with time, but you change it. You move from here to a different domain for your analysis, for the ease of your analysis, which is Laplace transforms. You move from the time domain representation to frequency domain representation, where the signal here now is a function of s, and s is what? S represents frequency. Okay, it's a complex frequency. So that was already explained to you, and I know that you guys are well aware about that. So yeah, let's see what is first. What is the transfer function? So what is the transfer function? Y of s divided by x of s, which is 2s plus 10 by s square plus 11s plus 28, right? So what do you have to do? I mean, this is the numerator, right? And this is the denominator. So what are the poles? Poles are what? Roots of the denominator. So what are the roots of denominator in this case? So xs is what? I mean, the denominator in this case is what? It is s square plus 11s plus 28. So what are the roots here? For that, what do you need to do? You have to equate d of s to 0, isn't it? So that gives you s square plus 11s plus 28 is equal to 0, which means that now if you do, this will be s square plus 7s plus 4s plus 28 is equal to 0, which gives you s into, I mean, this gives you roots is equal to minus 7 and minus 4, right? So these are the poles. So correct. The person who's all of you have said that poles are minus 4 and minus 7. That is correct. Exactly. Now what about the zeros? What about
5,
the
sir.
zeros? Yeah. So zeros are what? The roots of the numerator. Correct. So what are the numerator root? What is the numerator? It is 2s plus 10. How do you find the roots? Make it equate it to 0. So that gives you what? 2s plus 10 has to be equal to 0, which means s is equal to minus 5. So this is also correct. So this is actually the zeros of the system. So this was also correct. So the first one is correct. Very good. Now, is the system stable? So what is the criterion for stability of a system? This I didn't talk about in the recap.
In
So
a in a S plane, it should be lie on the left axis, sir, left half plane.
yes,
Uh,
good, very
it's
good. Yes, yes,
and
exactly. And what should lie on the left half of the x-axis? I mean, sorry, y-axis.
means it should lie on the left
What?
half
What?
plane.
It means what? It should lie means what?
Poles,
What should lie?
poles
Poles. Yes,
location should
exactly,
be.
exactly. Yes. So as was also explained in the lectures, if something goes to the right of the s-plane, it's a unstable system, right? So let's say this is your s-plane, okay, and as long as the poles remain in this side of this of the s-plane, okay, you are happy. So this is what this is sigma, this is j omega. All right. So as long as this the poles they remain in this side, you are happy. The signal will be, I mean the system will be stable. Okay. So since in this case the poles are -7 and -4, which will be somewhere here and somewhere here, -4 and -7, the system is indeed stable, right? It's a stable system. So this is also correct. Very good. Now what is the order of the system?
Second order,
Why do you say that?
based on the quadratic equation.
Hmm. So what is the what is meant what so in the lectures what did sir say about the order of the system? What was the meaning of the order of the system? I mean the answer is correct. It is a second order system. I do not deny that. I just want to understand whether you fully comprehend the meaning of this term or not, order of the system, or it's just that something has been said to you and you believe it. What is the order of the system? I mean, what is meant by the order of the system? What was explained to you in the lectures? Degree of the denominator. Yeah, how? Why? Exactly. So see, the formal definition of order comes from the this thing. The highest order of derivative, the highest order of derivative in the differential equation. Okay, in the differential equation which relates the input to the output of the system, that is what is the order of the system. It means that what is the you have to check what is the differential equation which relates this which relates input and output of the system, and what is the highest order of derivative in that particular equation, that is the order of the system. Since the highest derivative simply converts into the highest power of s in the Laplace domain, that is why you see that in this case the order of the system is second order, and generally the numerator is not the numerator's order, the numerator's power, s power, the power of s in the numerator will always be less, okay, or less or equal to the power of the s in denominator for any physically realizable system, and the reason for that is well explained in the lectures. So that is why it is generally the order of the denominator which gives you the order of the system, the order of the denominator which gives you the order of the system. So this is a second order system. Yes, it is the number of poles which is equal to the which is equal to the order of the system. Yes, you can say that. So this is a second order system. Good. So that concludes the first question. Any doubt here? I hope not. Moving on. Second question.
Sir, Sir,
Yeah,
for in terms of order, how it will impact on the stability and all, sir. For example, if you say the poles and zeros, now we can
mhm.
say based on that we can know the stability, right? If you know order, how what's in
Yeah. So that comes later. Okay, stability criterion comes later. That will definitely be taught to you. Please be patient slightly. Okay, and that will come. That comes weeks after today, probably in fourth or fifth week. Okay, so please wait till that time, because if I try to explain some everything now, then none of you will understand. I mean, I will also not be able to explain that at this stage. It is better
sir,
that yeah, yeah,
sir,
yes,
one more thing, sir. I mean, so analytically, we are finding the stability with the help of Paul's Laplace transform, sir, Laplace no, sir. In
yes.
if you go for high terms, how can we get in simulation softwares and all? How can we know the stability based on this? I mean, it will be related, or is there anything
No, it is
to know
related.
the?
Okay, and it is related. So, but again, all of that, the simulation thing will not be taught, will not be covered in this course. You can probably, uh, we can probably contact later. Okay, if you want to understand about simulation, you can probably contact me later. But right now, I will not be covering that. I will not be going into that, because that is not the not in the scope of this course. Okay, the simulation thing. Probably at the end of this end of the course, probably I will get one more hour extra. Okay, there you can probably ask this question, because now I will not be, and at this stage I will not be able to explain that. Okay,
Okay.
okay, fine. So the second problem. Hmm. So in this question is also same as the earlier one. So what is the transfer function T of S here between input and output? Yeah, come on. So it is y of s divided by x of s, isn't it? So it is s cube upon s cube plus 32 s square plus 49s plus 1 divided by s square plus 11s plus 28. So do you see a problem with this particular do you see any problem with this particular transfer function?
No, no, sir. In general, it should be zero pole should be present, right? But in this case, zeroth order is high.
Yeah, so what is the problem here? I mean, is there something wrong here? I mean, I
Uh,
have asked a question, third question, so there should be some point in asking that question, right?
yes, yes.
So what is the problem here? So you see, numerator has, as one of you pointed out, numerator's degree or numerator's degree is higher than the denominator's degree, right? Correct. Order of the numerator is higher than the denominator, right? So what will happen because of that? Because of that, if you keep increasing the this thing, the frequency of the system, frequency of the signal that you are feeding to the system, then there will come a time when as you keep increasing the frequency, the magnitude, the gain of the system will keep increasing, right? The transfer function magnitude here will also keep increasing, right? And at very high frequency, or let's say at infinite frequency, the gain will become infinite, right? The magnitude here will become infinite, correct? So that is not possible in a physically realizable system. As the frequency of the system increases, frequency of the signal which is feeding to the system increases, the system's response is not able to keep up with it. Okay, I mean, this is a general rule. Please understand, any physical system will only be able to respond till certain speed. After that, it will not be able to respond. So after that, the gain of the system will simply keep coming down. It will keep going down. So in this kind of a system where the numerator has a degree higher than the denominator is simply not possible physically. Okay. So the answer to this question is the system is not physically realizable. Yeah, Anil, you have raised your hands. You have a doubt? If you have a doubt, you can turn on your microphone and you can speak. Unmute yourself and you can speak.
No doubt, sir.
Okay, but you have raised your hand, so that is why.
सर फिर से एक बार एक्सप्लेन करिए।
ओके। तो मेरा ये कहना था यहाँ पे कि जो ट्रांसफर फंक्शन है सिस्टम का, जो कि यहाँ पे दिया हुआ है, राइट, आउटपुट लैपलेस ट्रांसफॉर्म y ऑफ s, ओके, और इनपुट जो है वो x ऑफ s है, और ट्रांसफर फंक्शन क्या बनेगा इन दोनों के बीच में, इनपुट से आउटपुट तक, तो y ऑफ s डिवाइडेड बाई x ऑफ s, ये बनेगा, राइट। हाँ, तो यहाँ पे जो सिस्टम का ट्रांसफर फंक्शन बनेगा वो बनेगा y ऑफ s डिवाइडेड बाई x ऑफ s, ओके। यहाँ पे ये मैंने लिख दिया है यहाँ पे, ओके। अब मैं ये कह रहा हूं कि ये सिस्टम फिजिकली पॉसिबल है या नहीं, मतलब ऐसा सिस्टम बनाना संभव भी है या नहीं, ऐसा सिस्टम बनाया जा सकता है या नहीं जिसमें ऐसा ऐसा सा ट्रांसफर फंक्शन दिखे हम लोगों को। तो वो नहीं दिखेगा, राइट संकेत?
यस सर।
क्यों नहीं दिखेगा? ऐसा सिस्टम नहीं बनाना पॉसिबल है, क्यों?
सर वो नहीं समझ में ही आया है इसलिए।
अच्छा, ओके। देखो, ऐसा सिस्टम इसलिए नहीं बन सकता है क्योंकि इस केस में जो न्यूमरेटर का ऑर्डर है, राइट, यहाँ पे एस क्यूब है, राइट।
यस सर।
यहाँ न्यूमरेटर का ऑर्डर क्यूब में है, इट्स अ क्यूब, वेयर एज डिनोमिनेटर जो है उसका ऑर्डर क्या है, एस स्क्वायर है, क्वाड्रेटिक है। ये क्यूबिक पॉलिनोमियल है, ये क्वाड्रेटिक पॉलिनोमियल है डिनोमिनेटर। तो इस केस में बेसिकली अब ऐसा मान लो कि लिमिट लिमिट इसका मैग्नीट्यूड अगर आप लोगे, ओके, इसका मैग्नीट्यूड लोगे अगर, तो मेरे को एक बात बता दो, इसमें अगर एस जो कि फ्रीक्वेंसी है, अगर एस को फ्रीक्वेंसी से रिप्लेस किया जाए, यही समझाया गया था, राइट, आपको, कि
यस
एस का मतलब लूजली आप फ्रीक्वेंसी समझ सकते हैं।
फ्रीक्वेंसी को
हाँ,
रिप्लेस कर सकते
करेक्ट करेक्ट करेक्ट। तो अगर आप फ्रीक्वेंसी से समझो इसका मतलब, और अगर बढ़ाते चले जाओ फ्रीक्वेंसी, तो ऐसा होगा ना कि ये न्यूमरेटर जो होगा वो डोमिनेट करने लग जाएगा एक टाइम के बाद, राइट। डिनोमिनेटर क्योंकि छोटा है तो न्यूमरेटर हमेशा बढ़ेगा, हमेशा बढ़ेगा,
यस
राइट।
यस
और बढ़ते जाएगा बढ़ते जाएगा बढ़ते जाएगा, एक टाइम के बाद ऐसा समय आएगा जब जब s विल टेंड टू इन्फिनिटी, तब ये जो भाई साहब हैं जो इस मॉड के अंदर हैं, उनका भी वैल्यू इन्फिनिटी हो जाएगा, राइट।
यस सर, समझ में आ गया।
हाँ, तो ऐसा सिस्टम जिसमें ऐसा, इसमें ऐसा दिख रहा है कि अगर फ्रीक्वेंसी एकदम हाई होगी तो इसका गेन भी बहुत हाई होगा। तो ऐसा सिस्टम बनाना संभव नहीं है एक्चुअली दुनिया में। ऐसे कॉपी पेन पे लिख सकते हैं, बट एक्चुअली बनाना ऐसा सिस्टम पॉसिबल नहीं है। क्यों नहीं है पॉसिबल? क्योंकि किसी भी फिजिकली रियलाइजेबल सिस्टम है जो कि संभव हो बनाना, उनका हिसाब किताब ऐसा चलता है कि एक टाइम के बाद वो एक स्पीड तक कोप अप कर सकते हैं कोई भी सिस्टम को। अगर आप कोई सिग्नल भेजोगे तो वो सिग्नल जो है एक सर्टेन स्पीड तक वो सिस्टम ट्रैक कर पाएगा, वो सिस्टम उसके साथ जो भी करना आप चाहते हैं वो कर पाएगा। लेकिन एक सर्टेन स्पीड के बाद सिस्टम को पता भी नहीं चलेगा कब सिग्नल आया कब चला गया, ठीक है। सिस्टम एकदम रिस्पॉन्ड नहीं कर पाएगा, सिस्टम सिग्नल को देख के, इनपुट को देख के। तो उस केस में you see, Hasi Rahman. Okay, so I was speaking. These sessions will be conducted in English. It's just that some of your colleagues have difficulty in understanding English, so that is why I was trying to explain them in Hindi. Okay, I have already explained this in English. You can, if you have missed it, you can go back and watch the lectures. I'll not be explaining it again, but yeah. So हाँ संकेत, मैं ये कह रहा था कि बेसिकली एक सर्टेन स्पीड तक ही सिस्टम ट्रैक कर सकता है सिग्नल। तो एक सर्टेन स्पीड के बाद, जो कि फ्रीक्वेंसी को डिनोट करता है, एक सर्टेन फ्रीक्वेंसी के बाद फिर सिस्टम का गेन जो है ना, सिस्टम का गेन ड्रॉप होता है। गेन का मतलब क्या हुआ? इनपुट से आउटपुट के बीच में जो ट्रांसफर फंक्शन का मैग्नीट्यूड है वो ड्रॉप होता है, वो जीरो तक चला जाएगा और कम भी हो जाएगा, ठीक है, जीरो तक चला जाएगा मतलब। तो इसीलिए इसमें तो ऐसा दिख रहा है कि हाई फ्रीक्वेंसी पे सिग्नल का गेन एकदम हाई है, सिस्टम का गेन एकदम हाई है। ऐसा नहीं होगा। आप समझ पा रहे हैं फिर मेरी बात?
यस सर, हो गया कंप्लीट।
ओके ओके, थैंक यू। Yeah, so this is, I guess this concludes the question here. Fine. So let's move on to the next question. Question number 3. Yeah, so this is a question which deals with the application of the op-amp. Okay, so first tell me, so this is an op-amp, right? For all the questions that I will be discussing today, assume that the op-amp gain is infinity. Okay, AV is equal to infinity, AV tends to infinity. Yeah, so first tell me what is the purpose of this circuit. You have already seen this in the lectures. So what is the purpose of this circuit?
Summer, sir.
Summer, right?
We are adding the
It is,
voltages.
yeah, it is adding the voltages. Which voltages is it adding?
Means in V1, V2, V3, V4.
Yes, exactly. Yes. Yeah, one of you has made it very precise saying that it is an inverting summer. Exactly, it is an inverting summer. The output will be negative of the sum of the input voltages. Okay, exactly. That's good. So it is an inverting summer here. Fine. Now tell me again. The next question, obvious question is, what is the output voltage V naught? So one of you have pointed out it's equal to minus 80 volts. So let's see whether that is correct or not. If others have any other answer, please tell me. Okay. So let's see whether that is correct or not. So what will be the output voltage V naught here in terms of the value R1, R2, R3, R4 and RF and V1, V2, V3, V4. So how will you solve this if you do not know the formula? So you just have to make sure that you understand, since this is a negative feedback, right? So do you identify that this is a negative feedback? You see the output here is connected to the negative or inverting terminal of the input of the op amp, right? So this is negative feedback. This is a negative feedback. So in this
Sir,
case, huh?
means if it is connected to the inverting terminal, how can we say exactly it is a, if they ask how can you say it is a negative feedback means?
Yeah, so that I explained just few minutes ago, right? Minutes ago I explained that. If that was not clear, please wait. Okay, in the probably in the next to next session you will be understanding what is negative feedback.
Okay.
Okay, one of you have commented that why do we need so many circuits, so many branches here and inverting op amp, op amp here, if we can simply make a summer by simply keeping things in parallel, right? So probably that was the question. Let's see. So why do we need an op amp here? Even if if we draw the output from parallel combination, we'll get the same current flowing. All right. So let's try to understand that question. So that's a very good question. It's a very good question. Let's address that first. Or before addressing that, okay. Before addressing that, let's first let's finish this question. I mean, what is the output voltage V naught? So since this is negative feedback, I'll answer that question. Okay. Why do we need this op amp here? Fine. So since this is negative feedback, what can we comment about the voltage at this point? Yeah, what is the voltage at this point here?
It's a
0
zero.
volt. Yes, because it is virtually shorted to the non-inverting terminal, isn't it? Yes. Yeah. So it is virtually shorted to the inverting terminal, non-inverting terminal here. So this is 0 volts here. Fine. Now, since it is 0 volts, how what happens to the? I mean, yeah. So what happens now? The currents, all the currents here will come and add at this point, right? At the junction here, and then they will be flowing through RF, isn't it? Correct? So what will that be? So we have, so what is IF? Oh, so direction is probably not correct. So this is IF. Yes. So IF is what? It is V1 upon R1 plus V2 upon R2 plus V3 upon R3 plus V4 upon R4, right? That is what it will be, right? Since the voltage what is the current? Current is the difference between the voltages between the two terminals of the resistor divided by the resistor value, right? So since one of the terminals here is anyway 0 volt, it will be V1 by R1 divided by V2 by R plus V2 by R2 plus V3 by R3 plus V4 by R4. That is fine. Now this current is going to flow through RF, right? Right. So what is V0 or V0? V0 will be V0 will be. Come on, guys. What is V0 in terms of IF?
RF by V1 upon R1 plus.
Yeah. So it is minus RF times IF, right?
Yes, sir.
Correct. So that is equal to how much? Minus RF times V1 divided by R1 plus V2 divided by R2 plus V3 divided by R3 plus V4 divided by R4. Correct. And how much is that if you put all the values here? So how much will that be? RF is equal to minus RF is equal to minus 20k multiplied by V1 is 1 volt divided by R1 is 1k plus V2 is 2 divided by 2k plus V3 is 4 divided by 4k plus 5 divided by 5k, and k and k cancel each other. So it will be 5 plus 4 is 9, 9 plus 2 is 11, and plus 1 is how much? 12. I hope I have not made any mistake, right? Right?
Yes, sir.
Yeah.
80 minus
Yeah.
6.
So 80?
Yes, sir. 2 will get cancelled. 4 will get cancelled.
Oh,
4 into 2,
that was
80,
the
right?
mistake. Yes. So it is minus 80, right? Minus 80 volts. Correct. Good. So the person who was saying that it's minus 80 volt is indeed correct. Okay. Now tell me, what is IF, current IF? What is the value of IF? Someone said it is 4 milliamperes. So is it 4 milliamperes? It is 4 milliamperes, right? I mean,
Yes,
the
sir.
current is simply the term in the bracket, inside the bracket, right? So it is actually equal to 4 milliamperes. Now, 4 milliamperes is fine. This is correct. But see, let's say that op amp here, the when you bought this op amp, it could only provide a current of 1 milliampere. Okay, I mean that is possible. So let's say the op amp is only, the rating is given that op amp can only provide 1 milliampere. It cannot provide 4 milliamperes. That is just not possible. It can only sink 1 milliampere. It cannot sink 4 milliamperes. So definitely you don't want the current to exceed 1 milliampere, right? If you exceed that current, nothing will work. So you want the current to be limited to 1 milliampere. So what should be done? If you want to limit the current IF to 1 milliampere, what can be done? And by the way, you do not want to change the value of voltage V0. Okay, you do not want to change that. You have to keep all the voltages same. Okay, but you have to change the current. So what can be done? So
Sir, there we can change the resistance if we means based on the equation only. I'm saying if
yeah,
IF based on the equation, if we increase the resistance value, then current will absolutely decrease, sir.
yeah. So which resistance do you intend to decrease or increase rather?
Uh, no, the R1 and R2, R3 both are, everything is
Yeah,
adding
so
over
you want
here.
to increase R1, R2, R3, R4. Okay, that is what you want
Yes,
to do.
yes.
Is that all?
Us-
So
Uh,
one of you has said that, a lot of people have said that you also need to increase RF, right? Because you do not want to change the voltage V naught. Mind you, that is what was the first requirement. You don't want to change the value V naught. If you reduce IF, okay, and if you do not change RF, what will happen? V naught will also change, right? V naught will
Yes,
reduce.
yes,
So if you
yes.
reduce
IF
IF, so you have to
same
definitely
amount we can.
increase RF,
Yeah,
right? And if you increase RF, and reducing IF means you have to increase the value of R1, R2, R3, R4. So if you want to reduce IF by 4 times, you have to increase all the resistances here by 4 times, isn't it?
exactly, sir.
Yes, that concludes the question here.
In that case, if that RF would be 80 kilo ohms and resistance will be 8 kilo
Yeah,
ohms,
yeah,
16
correct.
kilo
So
ohms. Yeah.
all the values, all the resistors will be increased by 4 times. Okay. Now coming to a question which was asked by your colleague about why do we need, I mean, why do we need this op amp anyway? I mean, if you simply want to add the voltages, you can simply put things in parallel, which is V1, V2, V3, V4. So, and if you simply keep them in parallel, then you can add it. So the person who asked me this question is how do you make, how do you want, what kind of a circuit are you thinking about? Vasanti, yes. Can you please unmute yourself and speak?
So here I was thinking if the input impedance is infinity, no current will be actually flowing through the op amp. So like the sum of all the currents from all the parallel branches will add up and it comes to the V0 terminal and it flows out.
Yeah,
So
it goes like this. Correct. It goes like this.
instead of
Exactly. Yes.
having the op amp there, why don't we directly have that wire? I don't
Oh,
see
okay, okay,
the
okay,
requirement of
okay.
an op amp.
Oh, okay, okay. So it was slightly different than I imagined. All right. So your question is like this. Okay. This is what you were asking, right?
Yes, sir.
And this is V naught. So tell me what will be the voltage V naught here?
So the output voltage of the op amp there.
No,
It
it will be
is
slightly different, right?
oscillate across RF.
It will be slightly different in this case, isn't it? It will not be that. So see, if you use principle of superposition here, which is I mean, in this case, what will be the voltage V naught here? How will you find out? Tell me. I mean, quickly calculate and tell me what will be the voltage V naught. This will not be exactly same as the one that we just saw just now. V1 by R1 plus V2 by R2. This will not be that way. It will be slightly different. Tell me what it will be. Quickly calculate. Yeah, everyone, quickly calculate and tell me what will be the value of V naught here in this circuit.
Sir, if we ground the VX terminal, sir, then it will be the same.
Yeah. So if yeah, good. So what so in this case you can clearly see that this will not be what you wanted, right?
Yes, sir. Yes, sir.
Yeah. So you want to make sure that this is ground. That is what you're saying. If it is ground,
Yes, sir.
but if it is ground, what will happen to the current? Can any current flow through this if there is a ground here?
No, sir. Everything will go to ground.
Correct. So nothing will go to the RF terminal, but everything will go to ground, right?
Yes, sir.
So that is why you want to make sure that this node voltage here is 0, but at the same time you do not want to put an explicit ground here, right? That is
Yes,
something which you do not desire. So that is why op amp is a requirement here, and op amp can make sure that this node here is pulled to 0 volt, but at the same time you do not need to explicitly connect a ground here. You understand?
yes, sir. Sir, I don't really understand how this functions as a summer. Sir, is it just because it adds up all the currents from all the branches there?
Yes, 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 yes.
Sir, but how is that actually a virtual short, sir? How do we know that it is a virtual short for an ideal op amp?
Yeah, so see, it's in a negative feedback, okay? And the meaning of negative feedback and how to identify negative feedbacks, probably that will be taught to you in the next week or next to next week, okay? Don't worry about it. Identifying whether a circuit is in negative feedback or not, that is in the syllabus, and you will be able to clearly distinguish between negative feedback and positive feedback and all kinds of feedbacks. But wait for that, okay? Right now, please just understand this, because now you will not be dealing with the questions of that kind that you will be confused. So just understand that if you see a connection between input and output, sorry, inverting, this is an inverting terminal, right? Minus, correct? This here is an inverting terminal here, and there is a connection, there is some connection between the input inverting terminal and the output here. And if you see such a connection, it means that the system is in op amp is in negative feedback, okay?
Yes, sir.
And if the op amp is in negative feedback and it's an ideal op amp, there will definitely be a virtual short. There is no denying that. There will always be a virtual short. Okay?
Yes, sir.
Yeah, fine. So I understand your all of your questions are based, I mean, really into the identifying the negative feedback. But see, that's something which was not covered in the lectures. So I cannot just go on and explain that, because that takes time. Okay. So it is there in the syllabus, that this will definitely be explained. If it is not, then I will be explaining it, okay? Don't worry about it. Or I will point you to the right direction where you can find the materials, find the lectures about it. Fine. Moving on. Yeah. So this is also almost the same. Yeah. So first tell me quickly. I will not be solving this question in exactly the same manner that I solved the earlier one, because this is almost the same. Tell me, what is the purpose of this circuit? Non-inverting summer, one of you has said. Yes, it is a non-inverting summer. All of you understand this is a non-inverting summer. In the last case, in the previous case, all the voltages here were connected to the inverting terminal, okay? And this was acting as an inverting summer. We also saw, right? There is a minus sign involved here, right? Minus sign here. But in the second case, I mean the present in this question, you see that all the voltages here are connected to, okay, this is V1, V2, V3. In this case, all the voltages are connected to the non-inverting terminal, okay? So that is why it's a, I mean, it will, if you do the maths, you will see that in this case you do not get a negative sign between V out and V1, V2, V3, okay? and I
So
encourage.
based on this, we can say it is a positive feedback, sir.
It's not a positive feedback. No, no, no. Why do you say that?
Uh, This output voltage and input voltage are in phase to each other, no?
No,
Not
no, no,
out
no,
phase.
no, no, no. The way to identify negative feedback is whether there is a connection between the input and output, or not. Okay, and the if there is a connection between input and output, you have to identify whether the connection is between the inverting input terminal, or the non-inverting input terminal. If the connection is between inverting input terminal and the output, then the system is a negative feedback. Or probably I will write that. Okay, you see, if, but please note that this is not a universal statement. This statement will falsify. This statement will fail the moment you go into complex circuits. Okay, I mean, this is just for this week, and please do not take it take it universally. Don't accept it just like that. This statement is very loosely formulated statement, just for the purpose of this particular class, for this particular week. So, I mean, a connection between inverting terminal. And what do I mean by inverting terminal? All of you understand? Inverting terminal means the negative of the op amp. Okay. It means that the system is in negative feedback.
सर तो वो पॉजिटिव फीडबैक किसको कहेंगे?
हाँ हाँ, बता रहे हैं, बता रहे हैं. So this is how it is. If you see a connection between the positive terminal, okay, positive input terminal, and the output, then it's a positive feedback. If it is between the negative input terminal and the output, it's a negative feedback. However, I must emphasize it. This, whatever I have written here, not okay. And I will show you several examples where this statement will fail. Okay, these statements will fail. You'll not be able to just say that it is a negative feedback or positive feedback just by looking at the connections. A lot of times you will see that the connections will be there both between the positive and the negative terminals. I mean, you can find a connection like this also. In fact, I will be solving such circuits later. There will be a connection like this also. There will be a circuit where there will be connections at both places. And here we will not be able to just say like that it's a negative feedback or positive feedback. That's difficult to say. You have to look at it slightly differently in that case. Okay, but for now, for this week, you can at least say that it's fine. I mean, this statement will work for this week. Okay, fine, fine, all right. So yeah, So it's a non-inverting summary amplifier, right? Now V0 you can find out, not a problem. IF you can find out. What can you comment about the virtual short notes of the op amps in problem 4 and 5? That's another question. Tell me. In this case, the virtual short nodes here, the plus and minus terminals here, they are both at ground, 0
सर ये
volt, right?
क्वेश्चन आप सोल्व करा सकते हैं, थोड़ा ये प्रॉब्लम हो रही है सोल्व कराने में,
कौन
इक्वेशन
सा
में।
सॉल्व कौन सा वाला सॉल्व कराना है?
ये वाला, हाँ।
ये आपके लिए है, ये हम चाहते हैं आप सॉल्व करें खुद से।
ओके सर।
हाँ, ये बिल्कुल लास्ट क्वेश्चन प्रॉब्लम नंबर 3 की तरह है, हम चाहते हैं आप खुद से सॉल्व कर लिए। हाँ, fine. So yeah, so I was saying that in the problem 3 you saw that when the non-inverting terminal here was grounded, so you saw that the this terminal here, the inverting terminal also equal to 0 volt, right? This is how the virtual short nodes were in problem number 3. But in problem number 4, you will identify that this and this voltage here, there will be some non-zero voltage, isn't it? Isn't it? Is everyone comprehending what I am saying? The voltage here will be some non-zero voltage, right? Yes, the voltage at this point here will be some non-zero voltage, okay? And because it's a negative feedback and the gain of the amplifier is very high, so that is why the voltage here will also be same as the voltage here, right? These two voltages will be virtually short. So, but compared to the previous case, in this case, the voltages here will be non-zero, isn't it? Now, this is a very important observation. You will see that because of this particular reason that the voltage here is non-zero at the input, and in the problem number 3, the voltage here was 0, inverting kind of amplifiers. Basically all the amplifiers which are inverting in nature, which are like inverting summer, inverting amplifier, all those, they are preferred over these circuits here are preferred over the circuits which are non-inverting in nature, okay, simply because the input at the input of the these op amps of the non-inverting amplifiers, okay, you will find non-zero voltages here, and this is something which is not desirable. You will able to appreciate it more when you are doing a high level course, okay. I just wanted to keep it here, just wanted to give that information to you. And these circuits are not used, sorry, these kind of circuits are used less compared to the circuits which are inverting in nature, because their input terminals are both equal to 0 volts. All right, okay. Now one of you asked me about problems where there are capacitors and in the op amp, and you find it difficult to solve. So let's solve this circuit here, and this is already solved in the lectures, but let's do it again anyway.
Sir, could you please explain in time domain as well?
In time domain, why not?
Hmm.
That's also fine. But you see, the whole point of moving to Laplace domain was that it becomes easier for you to handle, because in Laplace domain, differential equations simply convert into algebraic equations, isn't it? So
Exactly.
you can solve it in time domain, but just you can to make your life comfortable. That is this is the part that we took. The Laplace transforms were introduced only to make sure that the life becomes easier. Anyway,
Yes.
so first let's do it in Laplace domain only. But before that, what is the purpose of this circuit? It was already explained in the lectures also. So what is the purpose of this circuit?
Differentiator, right?
Yeah, it's a differentiator, right?
Sir, how do we know it's a differentiator?
Yeah, because I'll be doing the equations now. You'll be able to identify that this is indeed a differentiator. I just asked you because I thought that all of you have gone through the lectures, because this is directly taken from the lectures. Okay, this circuit is directly taken from the lectures, and the lectures, it is said that it is a differentiator. So I'll be explaining how it is a differentiator. Okay. Yeah. So let's solve
Sir,
it now.
sir, if I
Yes.
want, if it means based on the input current, if a capacitor based on the current direction, we can also we can say it is a differentiator, right? If a capacitor is present across the resistor and resistor is replaced across the capacitor, then
Hmm.
current will be different, right? So based on that, without writing the equation, based on that current while
You can
entering, we
say
can,
you, yeah, you can do that, but you see, this is, you are only able to say because you have solved it once. Okay, for the person who is seeing it for the first time, it might not be that trivial. Okay, they have to, for once, at least once in your lifetime, you have to write equations, and then when you write the equation and convince yourself, after that, whenever you see a circuit like that, you will be able to understand. Okay, but for the first time, you have to write the equations.
yes, sir. For without writing equations mathematically,
Yeah,
by if
mathematically only. Mathematically
it
only.
will
How do you find out? How do you say mathematically? You have written some equations sometime in your life, right?
yes, sir.
That is how you are saying mathematically.
Yeah, yes, sir. I mean, so interview means in interview, how can we explain that like that?
I understand all your concern, but see, uh, for that, that is what I'm saying. Now, you write it once, you will be able to understand. I will be giving you an intuition after that.
Yes, sir.
Okay. Hmm. But that intuition will only come because there's an inherent maths behind it. You just don't have to pick pen and paper. That's all. You'll be able to quickly say, but for that you'll have to look at the maths once in your life. Fine. So this is a differentiator. How is it a differentiator? You see, first of all, again, what kind of a feedback is this? Tell me.
The negative feedback.
Yes, it's a negative feedback. Exactly. So it's a negative feedback. Now, uh, now that we are clear on that, it's a negative feedback. So, what can you comment about this note here?
The zero voltage.
0 volts, yes. Arey yaar. All right. So it's a 0 volt here. 0 volt here. Fine. So now, what is the current that is going to move from here to here? Let's call it I in. What is the current here? I in. In Laplace domain only you have to answer. So it is Vi minus 0, right? Divided by the impedance, which is due to the series combination of C and R, right?
Sir, R plus 1 by CS.
R plus 1 by
CS.
SC, right? Yeah, CS or SC, whatever you say. You see, whenever I hear CS, I think about computer science department. Okay, so it's 1 over SC. Fine, it's 1 over SC, right? So all of you are clear on this, right? This is R plus 1 over SC. Input current, I mean impedance. So what is the current? VI divided by 1 plus SRC into SC, right? This is the current. Now what is the, so what is V naught? Tell me, what is V0? This same current, it flows like this, right? The same current flows like this, moves out. So what is this? It is minus R into Vi into SC upon 1 plus SRC. It's equal to minus Vi times SRC divided by 1 plus SRC, isn't it? Now, let's say this R was not there. Let's say this R was equal to 0. So what happens to this? What change happens if R is equal to 0? Small r is equal to 0, what happens to this V out here expression?
So Vi times S into capital R into C.
Yeah, it becomes Vi times SRC. That's all, right? Nothing else. And can you see that this is a differentiated equation, isn't it? I mean S in the okay. If V of t has a Laplace transform which is given by V of S, small v of t has a Laplace transform which is given by V of S, capital V of S, what is the Laplace transform of dV of t divided by dt?
So S times V of S.
Yeah, S times V of S, correct. So what I am saying is, in this case also, you see what is V out? V out here becomes equal to Vi times minus Vi times S times RC, right? So if RC is a simply some constant, RC is simply some constant, you see that there is an S multiplication, right, in Vi. So V out will be some kind, so if you try to represent it in time domain, it will be what kind of an equation? V of t will be equal to what? dVi by dt into minus of RC, right? This is how it will look like, isn't it?
Yes, sir.
Yeah, so this is a differentiator, but here I have made an assumption that R is equal to 0, small r is equal to 0, right? This is an assumption which I made. Now actually if you look into the differentiator circuit, the differentiator circuit doesn't, I mean ideally shouldn't have this R here, okay? This R, small r shouldn't be there. There should R value should be equal to 0, okay? But what happens is, if R is equal to 0, tell me what happens to the current here, I in. So if R is equal to 0, I in will be what? It is Vi times SC, right? Isn't it? Right? It is Vi times SC. So you will identify, you can observe that as the frequency increases, as S increases, the value of this current will also keep on increasing, right? This will keep on increasing, and V out, it will also keep on increasing, right? This V out voltage, since it is Vi times SRC, this will also keep increasing as S increases, right? So if you look at it in the frequency domain, if you plot its magnitude response, so you will see that VO and frequency S. So just as this is a very rough this thing, it is not a correct diagram that I will be showing, but still you will get the idea. You see that it will keep increasing like this. Let's call it omega. The magnitude of VO, it will keep increasing. The current also will keep increasing. Okay, the current I in will also keep increasing, something which is not desirable. I mean this will also keep increasing like this, right? So this is not desirable from practical point of view, because as frequency increases, if the current start to increase, I mean there will come a time when your op amp will simply not be able to provide that current, or probably the output voltage will become so high that probably the op amp might go out of saturation, the transistors might go out of saturation. Okay, so all these things you want to avoid, so that is why you put a resistor R here. What this resistor R does is, it limits the current. You see how it limits the current? See, if R is not equal to 0 here, what will happen at very high frequencies? What will happen? When S becomes very large, the denominator here will mostly be dominated by SRC, right? The one we can neglect, right? So at very high frequencies here, as S becomes very large, You see that what will happen? You will see I in will becomes equal I in becomes equal to
Saturation.
huh? Come again?
Sir, IN will become saturated at
Yeah,
different state.
correct. Vi times Sc divided by 1 Src, right? So that Sc gone, so it will become Vi by R, right? So it becomes saturated. It saturates after a while, and the current is limited. Similarly, the voltage here V out, it will also be limited, right? And that is in terms of this graph here, you will see that there will be a plateauing here. This will be limited after a while, and this is
सर ये R इक्वल टू जीरो वाला समझ में आ गया, पर ये ऊपर वाला है ना वो VASC डिवाइड बाय SRC वाला वो नहीं समझ में आया।
नहीं, मैं यही बता रहा हूँ आपको कि जैसे अगर R0 नहीं होगा, नहीं R0 होगा तो प्रॉब्लम ये है कि बढ़ते चला जाएगा, राइट? करंट बढ़ता चला जाएगा, वोल्टेज भी बढ़ता चला जाएगा। अब वो चीज
यस सर,
डिजायरेबल नहीं
पर
होता
वो
है।
1 + SRC में से आपने SRC से क्यों लिखा वो नहीं समझ में
ओ
आया।
अच्छा, यहाँ पे बहुत बड़ा S अगर हो जाएगा, S बहुत बड़ा हो जाएगा, बहुत बड़ा हो जाएगा,
अच्छा
तो
अच्छा, ओके ओके, समझ में आ
वन को
गया।
नेग्लेक्ट कर सकते हैं, राइट?
यस सर।
एस बड़ा होने का मतलब होता है कि आपने बहुत हाई फ्रीक्वेंसी पर काम कर रहा है, आप बहुत हाई फ्रीक्वेंसी पे काम कर रहे हैं, तो इसलिए मतलब एस बहुत बड़ा है, तो उसमें वन को नेग्लेक्ट कर सकते हैं, राइट? हाँ, तो वो वही लिखा है मैंने यहाँ पे. So this is what I was explaining. So in this case, that is why we add this resistance R here. At lower frequencies, this will still behave like a differentiator, but at higher frequencies, it will cease to behave like a differentiator. It will act like a non-inverting amplifier. Okay, sorry, it will act like an inverting amplifier at higher frequencies, and that can also be seen from this point here. At higher frequencies, here what will happen is at S very large S, what will happen is the gain will become V out here will become equal to minus Vi times R upon small r. Okay, are you getting it? So it's an inverting amplifier at higher frequencies, but at lower frequencies, still as S is when S is very low, it will still behave like I mean, if S is very low, you can neglect this term, right? I mean, the denominator will mostly be dominated by 1 if S is very low. So you can still assume that VO is equal to minus Vi times SRC, and there it behaves like a differentiator at lower frequencies. But at higher frequencies, it ceases to behave like a differentiator, but it starts acting like a simple inverting amplifier. So is that clear?
Yes, sir. Sir, could you please explain with the impulse input and unit step input or how that voltage waveforms?
Okay, that I will do in the next class. That will take some time. Okay, but we are running out of time. So only 3 minutes left. Okay,
Okay.
so I'll do it next class. Please remind me again. Okay, I'll definitely
Yes,
do
sir.
it. Don't worry about it. There is another problem number 6, but that is something which I want you to do. It's the instrumentation amplifier which was given in the class. I want you to derive the voltage V0 here. It is exactly the same circuit. Okay, the voltage V0 was also given in this in the lecture, but it was not derived. It was not explained how the expression from V0, how did we reach to that expression. So I want you to derive that expression for V0 in terms of V1, V2 and all the resistor component values. I want you to do that, and please do that. There is another question, problem number 4, where I wanted you to solve this, where I want you to solve this question yourself. Okay, so I guess that's it. That concludes our week 1 content. So I hope I will see you in large numbers in the next session also on Tuesday. Okay, so yeah, if you have any feedback, you can maybe say next time if you find it any difficulty in the lectures, or if you find any difficulty in the way tutorial was delivered, you can maybe tell that to me in the next session. Okay, Sir, can you
Yes.
please explain problem number 2 and 6 of week 1 assignment? We are not we are not this thing. We are not authorized to do that, and we cannot explain you the. We cannot solve the questions for you for the current assignments which are being given to you. Yeah, link for recorded lectures they will be given to you in the meantime in a while in due time.
Sir,
Yeah.
sir, why do we only take the Laplace transform of circuits and not the Fourier transform?
Yeah, we do take that Fourier transforms also, and it's just that Laplace transform is more generalized. Fourier transform is only for frequencies. I mean, j omega. You replace j omega with s, you will get Fourier Laplace transform. Okay, Laplace transform is more generalized. It is complex quantity. Fourier transform is only for real frequencies f. Whereas Laplace transform is more generalized transform. Okay, it takes into account frequencies which are complex.
Yes, sir.
Yeah. Fine. So let's meet again next Tuesday. Fine.
Sir, I'm
Yeah.
actually I am in analog ACDC last year we discussed now. From that time onwards, I need 5 minutes, sir. I have few questions regarding analog only.
Okay. So rest of
Uh,
you can leave and only he can maybe be here. Yeah. Yeah. So yeah, you can say what you wanted to ask. You can ask.
Uh, yes, I mean, recently I attended one interview, Max Linear, basics, everything I went, sir. Then they asked a few I mean, few amplifiers with a different connections, sir. He will say, and he is asking question points. How can you? What is your intuition and all in Max Linear?
Okay.
I get lag in that area. How can I improve, sir? Could you please recommend me any book? And I am a follower of you in LinkedIn as well. You remember or not? And
Okay.
I did course by Mon Mondal sir last semester, analog VLSI design.
Okay. Okay. Okay.
There also he discussed about a negative feedback. Will be that is sufficient or in addition I need to do
You
Nagendra
can
Krishnapur
maybe
sir.
yeah. Nagendra Krishna Purus's lectures. You can go through them. You can solve the assignments. Okay, that should be enough. If you have done it diligently, it should be enough. Don't need to do anything more than that. Probably if you want to go in deeper into certain topics, you can maybe find the lectures again on their website only, IT Madras. Okay, ICS website. You can find specialized topics. You can go deeper into that. But I guess if you want to only learn the basics, then probably the lectures provided by Nagendra Krishna Professor and even a lot of flavors of those lectures are available now by different professors of different IITs. Okay. In fact, this analog circuits was also one of it will almost be the same as that only. A few contents are lesser in this course, but I would say it doesn't matter if you go through any of these lectures, you will be fine. Go through the lectures, solve some questions, assignments, okay, and just don't memorize things, okay. Just don't believe someone is when they say something. Try to come up with reasoning for the same. Every statement that you make about the circuit, when you are designing something, when you are trying to solve some circuit, whenever you write a statement, whenever you come arrive at a solution, you should or not solution, not the complete solution, but any point in the solution, you should question yourself. Okay, why should it be like this? Why is it like this? What is the logic behind doing this? Okay, every question, every step, if you question yourself, you will be able to quickly develop that understanding. Okay, which is sought after in the industry. So it's okay. I mean,
Okay.
just go through those and I don't think there is anything much that I can do. There is no book that I can suggest here because books will again give you only questions, and again the questions
I mean,
are
at that time, actually, till basics everything goes well, sir. Afterwards, he asked me a dry inverter. Later and all, okay, discard the PMOS input and connect into